Have you ever stopped to think about what a home run, a firework, and a shooting star all have in common? I mean, they seem pretty different, right? Well, it turns out they're all playing by the exact same, really elegant rules of physics. So today we're going to dive into the world of projectile motion and uncover the simple secret behind everything that flies through the air.
All right, first things first, let's get a feel for what we're actually talking about here. A projectile is basically any object that's been thrown or launched, and then gravity is the only thing pulling on it. And once you know what you're looking for, you start seeing them absolutely everywhere.
You know, picture a soccer ball soaring towards the goal. It follows that perfect, graceful, predictable curve through the air. Yep, that's projectile motion.
Or how about a firework? It shoots up into the night sky, carving a path against the darkness right up until that big, beautiful explosion. That entire flight path, a textbook example.
And this doesn't just apply to things on Earth. Even something as amazing as a meteor, a shooting star, follows the same rules as it burns up in our atmosphere. At the end of the day, it's really just a rock falling under the pull of Earth's gravity.
Okay, so we've got a soccer ball, a firework, and a meteor. They seem totally unrelated, but they are all following one single, surprisingly simple hidden rule. So, what is it? What's the secret?
Let's get the official definition out of the way. Projectile motion is just the movement of an object where gravity is the only force acting on it. And the path it takes? That has a special name. It's trajectory. Now, just a little heads up. For this explainer, we're going to keep things clean and simple and ignore air resistance. That's a whole other can of worms.
All right, it's time for the big reveal. This is the master key, the one idea that makes this whole thing click into place.
And there it is. This is the big aha moment. What it means is we can take a complex arcing path and break it down into two super simple one-dimensional problems. The forward motion and the up and down motion are completely, totally independent of each other.
Think of it like this. A projectile's journey is like two separate stories happening at the same time. The horizontal story is kind of boring, honestly. The object just cruises forward at a steady, constant speed. The vertical story is all the drama. It flies up, slows down, stops for a split second, and then falls back down, just like if you dropped it straight from your hand. And the crucial thing is, these two stories don't interfere with each other at all.
So, if we've got these two separate, simple motions happening at once, how do they combine to make that elegant arc we always see? Well, let's peek under the hood and see how physicists actually describe this.
So this is what it looks like in the language of physics. On the left side, the horizontal motion, see that? Acceleration is zero. It's just constant velocity, smooth sailing. But on the right, the vertical side, you see that little g for gravity constantly pulling down. So what's the one thing that connects these two separate journeys? It's time. Time is the one variable they both share.
And when you plot these two independent motions together, when you combine that steady forward cruise with the constantly changing up and down motion, what shape do you get? You get a parabola. Every single time. This beautiful, predictable curve is called the trajectory.
Okay, so we've got the theory down. It's cool to know the shape is a parabola, but how do we actually go from theory to predicting its exact path? Well, lucky for us, there's a recipe for that.
It's a pretty straightforward four-step strategy. First, you break the initial launch down into its horizontal and vertical parts. Then, you treat them like two totally separate, one-dimensional problems. Step 3, you solve for what you need, remembering that time is the magic key that links them together. And finally, you just put the two results back together to get your final answer. It's a really powerful method.
So let's put this into practice. Let's say we have a fireworks shell. It's launched from the ground at a pretty speedy 70 meters per second and at a really steep 75-degree angle. Our mission is to figure out exactly how high it's going to go.
Okay, so we run the numbers for the vertical motion. What do we find? It's going to take exactly 6.90 seconds for gravity to fight against that upward launch and bring it to a complete stop, right at the very peak of its flight, what's known as the apex. So, how high is that peak? In those nearly 7 seconds, that shell will climb to an incredible 233 meters. To put that into perspective, that is taller than a 60-story skyscraper. And while all that vertical drama was happening, what was our boring horizontal story doing? Well, the shell was just steadily cruising forward. In that same 6.9 seconds, it traveled a horizontal distance of 125 meters. So now we can pinpoint exactly where that firework is at its highest point in the sky.
So why does all this matter? I mean, who cares? Well, this one simple rule,
Splitting motion into two parts doesn't just predict the flight of a firework. It unlocks our ability to understand and predict the physical world, from the arc of a quarterback's pass to the path of a mission to Mars. It's really all about predictability. And one of the most useful things we can predict is an object's range, which is just the sciencey way of saying how far it will travel horizontally. And you can imagine, in sports, in engineering, knowing how far something's going to go is often the most important question there is.
So what's the secret to getting the maximum distance? Well, if the launch speed stays the same, it is all about the angle. As you can see here, 45 degrees is the magic number. It's the sweet spot that gives you the maximum possible range. And here's a cool little physics party trick. Angles that add up to 90 degrees, like 15 and 75, will actually land in the exact same spot, even though they take totally different paths to get there.
Now let's take this whole idea and just push it to its absolute limit. This is a mind-bending thought experiment that Isaac Newton himself came up with centuries ago. See, we've been assuming the ground is flat this whole time, but we all know it isn't. The Earth is round. So what would happen if you could launch something so fast that the curve of the Earth itself starts to matter?
Imagine throwing an object with so much horizontal speed that for every single meter it falls downward, the Earth's surface curves away by that same meter. What would happen? Well, it would fall and keep on falling, but it would never actually get any closer to the ground. You wouldn't just be throwing a projectile anymore. You would have just launched a satellite into orbit.